Hello, class. In this video, we're going to be talking about the properties of logarithms. Remember that logarithms are these broad class of functions that represent the inverses of another type of function that we've already studied, exponential functions. So once we get to solving exponential and logarithmic equations, we're going to see that there are some interesting properties of logarithms that are going to help us sort of simplify the equation solving process so that we can have something that looks really complicated sort of packaged into something that's a lot nicer and neater and easier to solve. Okay, so if that doesn't make sense right now, it will here in time. So look forward to that in the next video. But for now, let's go ahead and introduce what these properties are and how to apply them. So first, we're going to review the definition of a logarithm, and then we're going to introduce these properties one to one, as well as demonstrate with a few examples how these properties work. Okay, so the first property we're going to learn about is the product property. Then we're going to move on to the quotient property, and then finally the power property. And after that, we'll be able to look at some problems that combine using these properties to take either multiple logarithmic expressions and combine them into one, or take one sort of bulky looking logarithmic expression and expand it into multiple smaller expressions. Okay, but without further ado, let's jump back into that review. So remember that logarithmic expressions, sometimes just called logs for short, are expressions that convey the exact same information as some exponential expression or equation. A logarithm uh, of the form log base b of y equals x can be converted to exponential form, and that looks like b to the x power equals y. Okay, so you have to remember some of this vocabulary that comes attached to exponentials and logarithms. And so you must remember, and I'm going to be asking you guys repeatedly, what is the base of this log function or the base of this exponential function? So in terms of an exponential expression, usually it's that big number that's written down below, and then the exponent x is a little superscript in the upper right-hand corner of the exponent. And then y either refers to the output of that exponential function if we're talking about an exponential expression. But in the context of logs, that little b superscript that's written below the word log, that's going to refer to the base of the function. The y that's inside the parentheses, that's going to be referred to as the argument of the log. And then the x on the other side of the equation is going to be referring to the exponent, okay? But again, these are like really two sides of the same coin. They convey the same information. And so you just need to make sure that you understand how to convert from one form to the other. And I think that using these couple of steps to guide you will help it become sort of a seamless process. So let's say that you're starting off with an exponential equation, and we want to convert that to logarithmic form by going through these following steps. First, you're going to have something that looks like b to the x power equals y. The first thing you're going to do is identify what is the base of this exponential equation. What is the base b? Okay. Then you're going to write the word log base b, or log with a little subscript rather, a little subscript b, whatever that number happens to be, and then a set of parentheses. Then you can go ahead and write an equal sign and then leave a blank because we're sort of preparing to swap some things around. Okay. So the log of the base matches the base of the exponential. Okay, those have to be the same, otherwise we've sort of messed up that problem. Then, if you recall that exponentials and logarithms are inverse functions, and when you have an ordered pair like x comma y in the world of exponential functions, then when we convert that to its inverse, that ordered pair is going to now become a y comma x, right? Where we swap the positions of those coordinates. Well, in the exponential equation, what we're going to do is take this x and this y and literally swap their positions in the equation. So when we go over to the world of logarithms over here on the right, we're going to put the y, whatever that happens to be, it could be a single number or it could be an expression, We're going to put that inside the parentheses, and then we're going to move the x over to the other side of the equation, like so. Okay, so we're essentially swapping the position of the x and the y values, and that's all you need to do. Okay, so always identify what the base is, then write log base b, open parentheses, equals, then just swap the position of the x and the y values, whatever those numbers or expressions happen to be. Okay, so if we use those simple rules, we should be able to convert things from exponential form and over to logarithmic form, but just understand that this arrow really goes both ways. So I could take something that's written in logarithmic form, take the base, and then swap the position of the y and the x so that I get my exponent up here, and then my argument becomes on the, or moves over to the other side of the equal sign. Okay. So we've done some examples of that in class and on some worksheets. So let's move over and continue talking about the domain of logarithms. Okay. So in a previous class, in a previous video, we looked at graphing logarithms, and then we saw that they produce graphs that look something like this. Okay. Remember, these are the inverses of exponential functions. So if you imagine a diagonal line that we call the identity function passing through your Cartesian coordinate system, your graph space, if you will, then if you flip an exponential function over that diagonal line, you will get a graph that looks like this, and we call this a logarithm. Okay. So this is just a general logarithmic function. We don't have to worry about what the base is now. All of our logarithmic functions look very similar, have some similar properties, but the domain of these logarithmic functions, assuming that they haven't been shifted left or right, will always be 0 to positive infinity. So if I look at the graph over here on the right, and I think about the domain of this function, that is asking how wide is this graph? So how far to the left does this graph go? Well, the blue line goes all the way to the left, but stops here at the vertical asymptote, which is at x equals 0. Okay, remember, this is our number line here, and our x value 0 indicates where this graph is stopping. Over to the right side of the graph seems to be going onward forever to the right, so we're going to say that goes all the way to the right to infinity. And so the domain of these functions are going to be from 0 to infinity, not inclusive. Okay. So what does this mean for evaluating functions in your calculator? Well, what this means is that literally the domain is the set of any input value you can plug in to the log function without breaking it, okay, without getting undefined or getting an error in your calculator. So I cannot put anything into this log function or into these log functions that is below 0. And also, remember, parentheses 0 means that 0 is also not a valid input for these logarithms. Okay. So if somebody were to ask you, what is log base 2 of -10, in other words, plug -10 into the log base 2 function and evaluate that, you should understand that that's going to be undefined. I'll just go ahead and write it here. Don't mind my terrible handwriting. Undefined. Because the function, this blue graph over here that we're looking at, doesn't extend into the negatives, right? This is where our negative numbers live, and -10 is probably somewhere very far out here, -10. But the graph itself doesn't go that far on the x-axis or on our number line. So that means that there's not going to be a corresponding y value. And so we're just going to say that this is undefined. Again, if you plug this into your calculator, you will see a log base 2 of -10 is going to give you an error. And so we're going to say that's undefined. Okay. Now, that error, if you're curious about it, when you get that error in the calculator, we'll say something like non-real number. Okay, so there is this more complicated branch of mathematics called complex analysis. And in that branch of mathematics, which is handled by mathematicians and grad students. There's actually a way that you can get around this error, and then that kind of involves imaginary and complex numbers. So for our class, that's going to be above our pay grade. We're not going to worry about it. Whenever we get a problem where they're forcing us to put a negative number inside a log function, doesn't matter what the base is, but if the input is a negative or if the input is 0, we're going to say that that's undefined. We're going to get an error in our calculator. We can't compute that, okay? So that's one of the first properties here of logarithms that we have to keep in mind. So if we're asked to evaluate, for instance, log base 7 of 0, well, we already said that 0 is not in this function's domain, right? There is a vertical asymptote here. So that means we're going to get an error. So we can say that this is also undefined. And I'll just go ahead and abbreviate it as undef. Okay? That's going to be undefined because 0 is not in the domain of this function. For the natural log of negative e, all I have to tell myself is that maybe I don't know what e is off the top of my head. Remember, that's Euler's number. It's a special cousin of pi. But if I have a negative e, which is approximately negative 2.718, that's still a negative number. I cannot plug negative numbers into any logarithm, including the natural log. So this is also going to be undefined. Okay. So just watch out for which numbers or which inputs you're giving or feeding to these logarithmic functions, because if it's not in the domain, you're not going to be able to compute a y value. Okay. So that being said, we can move on to our next property here, which is a really nice property. That is log base b of 1 will always equal 0. So regardless of the base, if you enter the number 1 as the input of your logarithm, then the output will always be 0. Okay? So what you might want to do is say, well, why is that true? Well, I think that seeing is believing. So let's just go ahead and maybe jump over to the calculator and just look at a few examples here. Okay. So I'm going to type in the log button, which remember, if you don't have a base, this is understood to be 10, base 10. Okay, so log base 10 of 1 is equal to 0. The natural log of 1 is equal to 0. And it doesn't matter what base I put in here. Remember, I can change the base if I have a TI-84 by pressing math. And then if I press the up arrow twice, I can find this log base function. And I can type in something like log base 2 of 1, where I have a base 2 function. But the output is still a 0. If I do log base 7 of 1, I still get 0. Okay. So it doesn't matter what the base is here. I can do something even more exotic like log base pi of 1. It's always going to give me 0 if I plug 1 as the input for my logarithm. Now that's kind of a curious property, and we might want to know where that comes from. Well, remember that our logarithms are related to, they're technically inverses of, but they're related to exponents. So let's think about this for a moment. For this first example, log base 2 of 1, we know this is equal to 0, right? We can understand this a little bit better if we make a conversion and go back to exponential form. Okay, so I'm going to put this in exponential form. And to convert this expression or this equation here to exponential form, remember, I'm going to write the base, and then I'm going to write the exponent, which is a 0. And then I'm going to swap the position of the 0 and the 1, so I get this equation. 2 to the 0 power equals 1. Well, if you remember your exponent rules, anything, any positive number, any negative number raised to the 0 power is going to give you a 1. There is one exception here. We never want to do anything where we have 0 to the 0 power, because that's going to be undefined. That's just a really weird case. But every other number raised to the 0 power is going to give you a positive 1. Okay, so Because that's true in the world of exponents, when we convert over to the world of logarithms, we get this natural extension, this rule log base b of 1 will equal 0 for that very reason. So in general, log base b of 1 is equal to 0 because if we were to convert that over to an exponential form, we would get the base raised to a 0, and anything raised to a 0 power is going to give you 1. So again, contains the same information as an exponent, just written in a slightly different, maybe slightly weirder form. Okay. Okay. There's another property that's really useful, which is if we have something log base b, and then the input that we're feeding the logarithm is also b, so the base matches the input, that's always going to give you a 1. Okay. We could test that out on the calculator ourselves by looking at some of these examples. So, pause the video and do this yourself if you'd like, but type in log base 2 of 2, you should be getting a 1. If you put the common log, log base 10 of 10, you're also going to get a 1. And then remember that the natural log has a base of e. So that's the same thing as log base e of e. So if you see natural log of e, if the base matches, then we're going to get a 1 there. Okay, so you might wonder, where does this property come from? Why is that so simple? Well, that's because if we take this expression log base b of b, so that if the input is the same as the base, and converted that over to exponential form, then we would write the base first, then we would swap the position of the exponent and the argument. So we have b to the 1 power is equal to b. And that's true because anything raised to the 1 power is itself, right? The exponent, as we sort of learned in grade school, means that we're repeatedly multiplying that number, that is the base. So if I have b to the 1 power, then I'm only having one copy of the base b. Okay? So whenever you see log b of b, that's always going to equal 1. So it'll probably help us simplify some stuff a little bit later on. Okay, this brings us to sort of the heavy machinery of these log properties. And the first one of these guys is called the product property. Okay, the reason why it's called the product property is because what we have inside this logarithm is x, y. And remember, that's the same thing as x times y. And we call multiplication a product. Okay, so if I have log of some base, and then inside the logarithm, I have x times y or something times something, and it doesn't matter how many things I'm multiplying, I'm allowed to then break that up into their own separate logarithms, but multiplication in the world of logarithms gets converted to addition. So if I have log base b of x times y, that's going to equal log base b of x plus log base b of y. Okay. So let's see this in action, maybe work it out on paper. So let's go over here to our trusted document camera and come up with an example. Okay. So the product property says, well, if I have something like log base 2, let's say we start with something easy like 3x. Okay. I'm not really doing anything with the 2 and the 3 here. What I'm trying to see is that the 3x is the same thing as 3 times x. So that means that I can split this up into two separate logs. So I'm going to write log base 2 of 3 plus log base 2 of x. Okay. In another example, if I had something like log base 3 of 4x to the second power y to the fifth power, then you have to remember that I have three things being multiplied inside this logarithm. I have the 4, I have the x squared, and I have the y to the fifth power. So this can be broken up into three separate logs since there are three things being multiplied inside the logarithm. So this is going to be log base 3 of 4 plus log base 3 of x squared plus log base 3 of y to the 5th power, like so. So again, I had 1, 2, 3 factors being multiplied inside the logarithm, and so I was able to split that into 3 separate logarithms. Okay. And all those logarithms will contain or maintain the same base. So if we start with log base 3, we need to remember to write that base 3 on each of these logarithms. Okay. And that should be a pretty straightforward application. Okay. So in the PowerPoint, I have one example here that you can look at. If I have log base 3 of 7 times u times v, 7uv, then that's going to be split up into 3 separate logarithms. Log base 3 of 7 plus log base 3 of u plus log base 3 of v. Okay, that went a little bit fast. Remember, go back and rewind this section and make sure that it makes sense to you before moving on. Okay. All right. The quotient property is this idea that sometimes we're going to get logarithms where inside the logarithm, the input is going to be a fraction or a division problem. So in this property, we have log base b of x divided by y. That's how you should think about this fraction, x divided by y. So if we have division, x divided by y, right? Then that's going to be converted into separate logarithms. We're going to have the same base on each of those logs, but we're going to separate them out where the thing that we had on top, the numerator, is going to come first, and that's going to stay a positive logarithm. But then we're going to subtract whatever factors are in the denominator. So we had a log base b of y at the bottom of our fraction, so that's why we're subtracting it, okay? Okay, so let's maybe take a look at some examples of applying this quotient property. So to apply the quotient property, we might have something like log base 5 of, let's go with z over 3. Okay. Well, because this is a quotient or this is division, I'm going to separate these two things, the numerator and denominator, into 2 separate logs. So I'll have log base 5 of z minus, because we're dividing here, log base 5 of 3. Okay. Here's another example. Let's say I had the natural log of e over xy. Okay, this fraction's a little bit more complicated, and my recommendation is that when you have a little bit more complicated factors inside the parentheses of that logarithm, then you should count the number of factors that are being multiplied. So like on this numerator, I just have e, which remember is Euler's number. So first, I'll start off with ln of e, and that's going to be the first thing that I separate out. But then in the denominator of this fraction, I have x times y, and that's 2 separate things in the denominator, 2 separate factors that are being multiplied together. So that means I'm actually going to subtract 2 logarithms here. First, I'm going to subtract the natural log of x, and then I'm going to subtract the natural log of y. Okay. We can take this one step further because the natural log has an understood base of e. So using that property that if the base matches the input, this is going to equal 1, we can simplify this to just 1 minus the natural log of x minus the natural log of y. Okay. So if that went a little bit fast, just go back and remind yourself, or go back and rewind the tape, run through it again, just until it feels a little bit more familiar, right? And you're going to get some practice in the homework, so don't despair if it doesn't make sense upon initial viewing. You're probably going to have to get some practice, watch it a couple times, but then it'll start to make sense. Okay. The last property that we're going to look at here is called the power property. And in the power property, we have a logarithm, log base b, but then the input itself has this exponent n. Okay. So if we have something raised to a power inside the logarithm, because logarithms are themselves conveying some information about an exponent, then this is like we have an exponent stacked on another exponent, okay? And the way you want to think about this is if you have an expression or a factor in here that has an exponent n, you can move that n to the front of the entire expression, and you're going to have n times whatever the logarithm of x is, okay? So let's take a look at a couple of examples of that just so we can get a handle of it, okay? So this is called the power property because if we have something like I'm just going to use the common log base 10 of x to the fifth power, then what we can do is just take this fifth power, move it to the front of the log, and this is going to be equal to 5 times just the log of x, okay? So we're just moving that exponent to the front and multiplying it, and then that's going to help us solve some equations a little bit later on, but we'll cross that bridge when we get there. Let's look at another example. 6. If I have something like log base 7 of, let's go with u to the third power, v to the fifth power. Okay. Then here I can start to combine some of my log rules, and this will turn into two separate logs because I can use my product property to break this up into two separate logarithms. So I'll get log base 7 of u to the third power plus log base 7 of v to the fifth power. And then I can go ahead and apply my power property here and sort of move that exponent to the front. So this one will become log base 7 of u, and we move that exponent to the front. Plus, we'll take this exponent, move it to the front of that expression, and we'll have 5 times log base 7 of v. Okay. So, like I said, you guys are going to run into similar, let's see, you're going to run into some similar problems in the homework. So, don't despair if this feels like it's going a little bit fast. When you get some practice in the homework, this is going to start to make a little bit more sense. In the next video, we're going to start solving some exponential and logarithmic equations, and we're going to start using these properties, so it's going to make a little bit more sense how and when to use these properties.